Right now, across thousands of distributed servers, unimaginably vast streams of human language are being digested into a single, massive statistical engine. The engine doing this processing is a base model. Stripped to its absolute essentials, this is a decoder-only transformer scaled to immense proportions, engineered to do exactly one thing: predict the next token. This is the autoregressive maximum likelihood objective. Given a sequence of text, the model calculates a probability distribution for the next fragment, assigning the highest probability to the token that actually appeared in the training data. To achieve high accuracy, the model must minimize its prediction error. If it cannot correctly predict that Paris follows the capital of France is, its mathematical loss increases. Because almost any form of human knowledge can be encoded as text, the most efficient way to reduce this error is to internalize the underlying facts, logic, and syntax that produce the text in the first place. This forces the model to acquire diverse skills: learning arithmetic to continue an equation, programming syntax to finish code, and movement patterns for chess transcripts. This approach breaks the traditional labeling bottleneck. There are no human labelers tagging right and wrong answers. Instead, the system is self-supervised. 1 trillion words of raw internet text provide 1 trillion free training examples, because the correct answer at every position is simply the next token already present in the text. Building a functioning AI assistant happens in 3 distinct phases. First is pre-training, creating the base model. Next is alignment, tuning it to human intent. Finally, prompting, acting on specific instructions. In this video, we focus entirely on phase 1, pre-training. At this stage, the model is only a fluent text completer. If you ask it, "What is the capital of France?" it might answer Paris, or it might generate, "What is the capital of Germany?" since it only mimics the pattern of quiz lists found on the web. The base model is a compressed statistical representation of human language. Turning this massive engine into a usable assistant requires solving a sequence of immense physical and computational challenges. Before the model can predict anything, it needs data it can compute. Computing raw individual characters creates sequences that are too long for efficient processing, while whole word vocabularies cannot handle rare or novel terms. Subword tokenization slices text into irregular chunks. Common words stay whole, rare words break into fragments. Using byte pair encoding, the algorithm merges frequent adjacent pairs, building a fixed vocabulary of word pieces from the bottom up. These tokens are the fundamental unit of measurement for the model. As a rule of thumb, one token equals roughly 3/4 of an English word, or about 4 characters. This choice dictates the model's constraints. A context window, the amount of text the model can see at once, is a strict token budget. Similarly, API providers charge users based on the total number of tokens processed. This creates a concrete disparity in language access. Tokenizers trained primarily on English fragment many other languages into far more pieces per word, meaning users of those languages pay more and fit less information into the same context window. Tokenization also explains common model quirks. If you ask a model to count the R's in strawberry, it often fails because it never sees the individual letters. It only sees the integer IDs for the blocks straw, aw, and berry. Tokenization is a design choice that sets the boundaries for a model's linguistic fairness, its deployment cost, and its fundamental capabilities. Because a model is a compression of its training data, its final knowledge and reasoning patterns are determined by the quality of the ingested corpus. We are currently facing a data wall. The supply of high-quality human-written public text is finite, and frontier models are already consuming a substantial fraction of it. Petabytes of raw web scrapes pass through a multi-stage curation funnel into a dense corpus. Quality filtering drops spam and machine-generated junk. Deduplication removes repeated documents, preventing memorization and saving compute. Contamination removal strips out test benchmarks, ensuring honest evaluation. Finally, these sources are mixed in chosen proportions. This mixture shapes specific capabilities. For example, increasing the ratio of code in the training set has been shown to improve the model's general reasoning and logic. Scaling laws prove that data quantity must grow alongside parameter count. However, recent research suggests that a smaller, higher quality dataset can often produce a stronger model than a larger, unrefined one. The data curation pipeline serves as the primary lever for performance. Even a massive neural architecture will fail to generalize if it is trained on noisy or redundant information. Training a frontier model is one of the largest computations in human history, requiring thousands of accelerators working in concert inside specialized data centers. The memory requirements for this scale are immense. While a high-end GPU might hold 80 gigabytes of VRAM, the training state for even a modest 7 billion parameter model exceeds 100 gigabytes. No single device can hold the model, let alone train it. The solution is 3D parallelism, splitting the workload along 3 axes. Data parallelism replicates the model across devices to process different batches. Tensor parallelism fractures weight matrices across chips. Pipeline parallelism distributes different layers like an assembly line across the cluster. Techniques like zero sharding further reduce memory overhead by partitioning the optimizer state across the entire cluster rather than replicating it on every device. This base model is the physical outcome of thousands of GPUs working in perfect synchronization, managed by a sophisticated distributed systems architecture. Pre-training is a massive one-time sunk cost, but inference, serving that model to millions of users, is a continuous expense paid every time a token is generated. In aggregate, inference costs often dominate the lifetime compute budget of a deployed model. Autoregressive generation is inherently sequential. To produce a response, the model must perform a complete forward pass for every single token it generates, making long responses computationally expensive and slow. To solve this, engineers use the KV cache. Instead of recalculating relationships for every new token, earlier tokens are stored and reused. This transforms the computational cost from a massive quadratic curve into a flat, manageable linear line. However, the KV cache consumes significant memory as the context length increases. This physical memory requirement acts as a hard cap on how long a conversation the model can maintain. Quantization is the second major lever for deployment. It involves compressing the model's 16-bit floating point weights into smaller 8-bit or 4-bit integers. Using lower precision arithmetic drastically reduces the VRAM footprint and speeds up generation, while preserving nearly all of the model's predictive accuracy. Quantization shrinks a 70 billion parameter model from 140 gigabytes down to a deployable 35 gigabytes, making it possible to run large models on consumer-grade hardware. We have traced the journey from the simple objective of next token prediction through the challenges of tokenization and distributed hardware to the final optimizations required for global deployment. While we have successfully engineered a powerful statistical engine, the base model remains a raw text completer. Turning it into a safe, helpful assistant requires the final critical stage, human alignment.